What the heck?
Took on
Wacky Calc Wednesday!
So remember what I said? I said that the Lambert W function, at least on the principal branch, is analytic on the domain, the entire complex plane minus this branch cut right here. Sorry, negative 1 over e is included. So this is where the principal branch of the W function is analytic. And since we're only talking about the principal branch, I'm just going to remove that. And remember, we proved this. Plugging in the conjugate of a complex number into the W function results in the conjugate of the output, at least on the principal branch. As well, we have that the derivative of the Lambert W function is equal to the Lambert W function divided by z times 1 plus the Lambert W function. So those three facts we're going to need to prove the integral now. And let's talk about the contour we're going to use. So we have ourselves the complex plane, right? So this is the real axis. This is the imaginary axis. Now to draw my contour, I'm going to use a different color. Let's use red. Ooh, my old Expo markers. Let's hope this works. So what we're going to do is we're going to have this feels very weird to hold now. So we're going to have what's called a keyhole contour, because it's going to look like this. So we're going to have a circle of radius r centered at the origin, and then it's going to loop around like so. It's a perfect circle centered at 0, and we're going to have it come around and then sort of hug the negative real axis like so until we get to negative 1 over e, where it's going to loop around that point and create this sort of keyhole shape. So we have, remember, our function is going to have two poles. It's going to have one at 0. Remember, we had t on its own in the denominator of the integrand before, and then some other point z, right? This point z is going to be what's going to determine the value of the function. So this is the origin, 0, and this is z, right? And this is a circle of radius r. And this is a circle of radius little r. And this exact point right here is negative 1 over e. And so the idea of this contour is that big R is going to get infinitely large. So essentially this circle is going to get infinitely large, and little r is going to get infinitely small as it approaches the point negative 1 over e. So essentially what we're doing is we're going to reduce this to an integral that happens along this branch cut. Because remember, on the principal branch of the W function, there is a branch cut at negative 1 over e all the way to, this is a branch point, and all the way to negative infinity is the branch cut. And so this integral will then essentially become a very, very large circle that loops around and then goes along over the top of the negative real axis, around negative 1 over e, and then along the bottom of the negative real axis, and then looping back around in the circle. So what is to be expected is that the integral over the big circle goes to 0, and the integral over the little circle goes to 0, and we're left with these two straight line integrals, which will result in an improper integral from negative infinity to negative 1 over e of this weird function, and then we'll be able to show a very, very amazing integral representation of the Lambert W function. So we know the contour we're going to use, we know the poles of the function, so let's just do what we did before with that fancy integral that I talked about before. So we're going to call this, we'll call this big circle, little gamma of big R. We'll call this little circle, little gamma of little r. We'll call this straight line up top, we'll call this C1, and we'll call this straight line on bottom C2. The entire contour is called C. Okay, I hope that's clear. And remember, we said that the contour over C of x times the derivative of the original function, which is x times e to the x, divided by this original function, which is again x times e to the x, times the quantity x times e to the x minus z, dz. We can cancel the x's and take the derivative of x times e to the x, but essentially what it comes down to is you make the substitution with x equals w of t, and you end up with this integral here. And I keep forgetting the 1 over 2 pi I out the front. Sorry about that. And we end up with the integral, if we do the substitution of x equals w of t, we end up with the integral 1 over 2 pi I times the contour integral over c of w of t divided by t times the quantity t minus z dt. And this integral is what we're going to massage into the very complicated looking and beautiful integral that we've all seen on the Wikipedia page that has very rarely been demonstrated. I'm more or less doing an explanation that's found in the article that I left in the description, and I also left the article to the Stack Exchange, or I left the link to the Stack Exchange question that helped me establish this result. So this is, of course, a closed contour, a simple closed curve, and so we have to take a look at the two loops that we expect to go to 0. And so we can sort of write this out as a sum of these 4 contours. I'm not going to keep rewriting this integrand for now, so just be cool with that. So we have this common factor of 1 over 2 pi I out the front. And of course we have the integral over the large loop. So we have the integral over gamma of big R, and I'm just going to write dt. This is not an integral over 1. Remember that. This is just the integral over this integrand here. I'm just not rewriting it again and again and again. So there's never going to be an integral over 1 in this video. So whenever I write this, just think this should be there. I'm just not rewriting it. And then we have the integral, which will go from, now we have to be really careful here. We're going from negative capital R plus I little r to negative 1 over e plus I little r. So that's a little confusing, but here, I'll write it out. So we're going from negative capital R plus I times little r to negative 1 over e plus I times little r of this integrand, right? And then we do this little loop around this tiny little radius circle, so gamma little r. And again, I'm not going to write the integrand, but it's implicitly there. And then we have this second straight line integral, but now this is looping around like this. Remember, this is being taken in the positive sense, I should probably specify, right? We're going counterclockwise around the curve, like as is tradition. In the usual positive sense, we're going around counterclockwise. And so this second line here is going to go from negative 1 over e minus I times r to negative capital R minus I times r over that same integrand, right? So we've essentially broken down our closed loop contour integral into these 4 pieces. And it's going to come down to showing that these 2 parts go to 0, and then these 2 combine in a really, really beautiful way that involves the conjugate of the W function, which is why we're going to need this fact. So this is all very symbol heavy, I understand that, but we can make it through. So I'm going to erase these things now. Now that we have this image in our head, I'm going to parameterize these 2 curves, and we're going to see if we can more or less, even if it's just heuristically, more or less show that these 2 things go to 0. And then we're just going to be left with these 2 straight line integrals. And how they go to 0 is because capital R is going to infinity, and little r is going to 0, right? Those are the 2 assumptions. But we'll have to actually do that as the last step. What we first need to take a look at are these 2 integrals here. So we need to sort of behave as though we haven't let capital R and little r go to infinity and 0 respectively yet. So let's just take a look at those 2 things first, and then we will talk about the contours, the circular contours going to 0. We know that at the very least there's these 2 integrals that are being part of this, and then we'll show that the 2 circle integrals go to 0. So we have the integral from negative r plus I times little r to negative 1 over e plus I times little r, right, of w of t over t times t minus z dt. That's the upper half, that's the upper line part, right? That's the upper half above the negative real axis. And then we have to add the integral that's underneath the negative real axis, which goes from negative 1 over e minus I times r, little r, to negative r minus I times little r of the same integrand. And of course we have the factor of 1 over 2 pi I out the front, right? That's not going away. And so now what we can do is really quite ingenious. And it took me a while to, because there's a step in the paper that I linked to that sort of just brushes aside the fact that you can utilize the conjugate fact about the W function, that plugging in a conjugate gives you the conjugate of the output. And it took me a while to realize how to establish that, because my impression was that we should first let these 2 quantities, little r and big R, go to infinity and 0, or 0 and infinity, respectively. But you actually don't want to do that yet. You actually want to do a substitution for these first. So in this integral, we're going to do the substitution of t minus I times r. So we're letting t become t minus I times r. Now remember, t is the dummy variable here. And now r is not going to 0 yet, which is to say that r is a fixed value for the time being. So when we do that substitution, the derivative of this is still 1, so dt is still dt. There's no change there. All that's going to happen is that this upper bound is going to become negative 1 over e, because this positive IR and this negative IR are going to cancel, and this one's just going to become negative capital R, again because the positive and negative IRs are going to cancel. And then these t's are going to change on the inside as well. For this one, we're going to do a similar substitution, but we're going to do t becoming t plus IR to cancel with the negative IRs in the exact same way. So doing these two substitutions, we end up with 1 over 2 pi I times the integral from negative capital R to negative 1 over e of w of t minus IR over, now this is going to be a very big denominator, t minus IR times the quantity t minus IR minus z dt. And now we have this similar looking integral from negative 1 over e to negative capital R of a very similar looking integrand, so w of t plus IR divided by t plus IR, the quantity, times the quantity t plus IR minus z dt. Now this looks very symbol heavy like I said, but it's all about to beautifully simplify. So what we're going to do is we're going to make this negative and switch the bounds so that it goes from negative big R to negative 1 over e, right, just like the other integral. And now what we're going to do is a beautiful, beautiful utilization of the conjugate fact. Because what are these two numbers, t minus IR and t plus IR? They're conjugates of each other. Yeah, okay, so here's the argument that I'm going to make, and people can feel free to correct this if it's not correct. Now that we've made these substitutions, these two integrals are going from negative capital R to negative 1 over e, which is a straight, and we established from the image that these will just be straight line integrals along the real axis, which means that t is only over real numbers at the moment within the context of these two integrals. So r is a real number because it's the radius of a circle, z is maybe a complex number, but t in these instances now has to be a real number because we're doing a straight line integral along the real axis from negative capital R to negative 1 over e. So these two numbers are actually complex conjugates of each other. So I can rewrite t plus IR as t minus IR like so, correct? I'm sorry, so I can rewrite t plus IR as the conjugate of t minus IR, like so. But what have we established already? If we plug in the conjugate number into the W function, we get the same thing as the conjugate of the output. So that's really interesting. But remember, the W function is just some real number plus some real number times I. And the conjugate of that is going to be that same real number minus that same real number times I. And when you take a complex number, x plus iy, and you add it to its, or I'm sorry, you subtract it from its conjugate, minus. So subtract it from its conjugate like so. What do you get? You get x minus x, which is 0, and you get 2iy, right? You get 2iy, which is to say you get 2i times the imaginary part of that number z, whatever it is, right? Now, we're going to show that the two circular contour integrals go to 0 when big R goes to infinity and little r goes to z. We're just going to let those two things happen now to watch the beauty happen. So we're now going to let big R go to infinity and little r go to 0 to see what it does to these two integrals, which remember are the integrals over the straight line portions of the keyhole contour. And what happens when we do that is we end up with 1 over 2 pi I times the integral, or times the big quantity, which contains the integral from negative infinity to negative 1 over e. Well, now look what happens. All the little r's, now they're not impacting now they're not the bounds of the integral anymore. They're just these little parts in here. And so as little r goes to 0, this goes to 0, that goes to 0, and that goes to 0. And we're actually just left with the integrand that we had before. W of t over t times t minus z dt. And the exact same idea is going to happen here. So we're going to get minus the integral from negative infinity to negative 1 over e of the conjugate of w of just t, right? Because negative IR is going to go to 0 as little r goes to 0. So we get the conjugate of w of t divided by t, because plus IR also goes to 0, And so it does there. So we get in the denominator, we get t times t minus z dt. And the beautiful thing is that not only are the bounds of these two integrals the same, but the denominators of the integrands are the same. So when we put them under the same integral, we don't just have to put them under the same integral, we can write them as the same fraction. And so we end up with this beautiful result, or a beautiful conclusion at least, that this is equal to 1 over 2 pi I times the integral from negative infinity to negative 1 over e of w of t minus the conjugate of w of t divided by t times t minus z dt. But what did we just establish before? When you add a complex number and its conjugate, when you subtract a complex number and its conjugate, you end up with 2i times the imaginary part of that number. Now, that means we can rewrite this top part as 2i times the imaginary part of w of t, right? Just like that. And what happens now is this 2i and this 2i cancel, and we're left with the integrand is now just the imaginary part of the w function over t times t minus z, and we're just left with 1 over pi on the outside. Right? So this, once we've let big R go to infinity and little r go to 0, this is what those two integrals over the straight lines, essentially around the branch cut of the principal branch of the w function, that's what those two come together to make. And it took me a little while to realize this little substitution trick here. It seems so simple in hindsight, but I was racking my brain as to why you could just make this the conjugate, and why this one would be allowed to stay the same, and how these bounds for the integral became the same, and you could just combine them. And it took me a while to figure that out, that simple little solution, but now I have it, and so those two will amount to this. And so once we prove that the two circle integrals go to 0, we can show that this is the only thing we need to worry about. But let's remember, what did we actually show that the integral over something like this is equal to? Remember, when we were talking about a general function f of x that had f of 0 equals 0 and a perfectly well-defined inverse, we showed that it was equal to this weird integral. We showed it was equal to that function f inverse of z divided by z. So all in all, we're going to end up, once we show that the two circle integrals are 0, that this is equal to the inverse function, w of z, divided by z, which is going to give us an integral representation of the w function, which is exactly what we're after, and as you will see in the thumbnail, and as I will link to in the description. I know this is long and symbol heavy, but the conclusion is absolutely stunning. So let's continue. Let's investigate those two circle integrals. So one of them I'll be able to explain pretty all right, and the other one I'll have to sort of just say it's an asymptotic relationship. That's why it goes to 0, because I don't have the full details hashed out, and I think this video is getting long enough. Perhaps try it yourself. So if we take a look at the circle integral, they're both circle integrals, the larger circle integral, so the one on gamma of big R, the big circle of the integrand on the inside, right, whatever that is, we understand that it's going sort of in the counterclockwise fashion around like that. So let's let t be replaced with r times e to the I theta, because that's a perfectly valid way of representing complex numbers on a circle of radius capital R centered at the origin because of Euler's formula. And that tells us that dt is going to be equal to I times capital R times e to the I theta, because this is with respect to theta, times d theta, right? And the big circle arc was sort of starting at negative pi and going around to positive pi, right? A big counterclockwise circle. And so it's essentially going to be this integral. So from negative pi to positive pi of w of capital R times e to the I theta divided by capital R times e to the I theta times capital R times e to the I theta minus z times the replacement for dt, which is capital I times R times e to the I theta. Did I say capital I? I just meant I. I times capital R times e to the I theta d theta. So as we can see, these nicely cancel, and we're left with the factor of I, but notice we have something that's essentially asymptotic to capital R, which is a linear term, right? So as R goes to infinity, this is going to grow linearly. It's not too hard to see that the w function, or actually each branch of the w function, so w sub k of this, is asymptotic to the similar kth branch of the natural logarithm, which is of course equal to log z on the principal branch plus 2 pi I k, right? So when k is 0, this goes away. This is the principal branch of the logarithm, and that. So because we're on the principal branch, we can just say k equals 0, and so we don't need any of that. Essentially, what I'm saying is the Lambert W function is proportional, or not proportional, asymptotic to the Lambert W function is asymptotic to the natural logarithm, which means as r goes to infinity, the top of this fraction is going to look a lot like the logarithm of capital R, whereas the bottom of this fraction is going to just look like r. So this is going to look like, as r goes to infinity, much more like the integral from negative pi to pi of log r over r d theta, right? And I know that there's theta inside there, but the size of e to the I theta is always 1, and so this is really going to be depending on r. And that's essentially saying like the size of it is going to look like that, and I'm using very, very loose notation here, but hopefully you're sort of understanding what I'm saying. And because r as a linear function grows much quicker than ln of r as a logarithmic function, the size of the integrand is going to go to 0, which means any integral over something that goes to 0 is also going to go to 0, so this goes to 0. That's essentially the argument as to why the large circle goes to 0. So that's the first part. And then the argument as to why the integral over the little arc goes to 0 is slightly more complicated, and it's a different asymptotic relationship. I will link to the paper, like I said in the description, and feel free to use that as a resource. It's a wonderful paper, but you essentially want to parameterize it in the same way using this parameterization. So t equals little r times e to the I theta minus 1 over e, so that you center it at minus 1 over e, which means dt becomes I times little r times e to the I theta d theta, and little r goes from negative pi over 2, because it's going clockwise, it's going to go from pi over 2 to minus pi over 2. I know that that's opposite, but I'm saying that it's going in that direction, right? The integral starts at pi over 2 as the bottom index and goes to negative pi over 2 as the upper index. So you can use negatives to flip that around. The point is that's the order that it's going into. You need to make a different asymptotic argument because as w approaches 0, it has a different asymptotic relationship than when it goes to infinity, but it also works out in the end that that integral over the little circle does in fact go to 0, which means that we can conclude this relationship here, that w over z, w of z divided by z, is equal to this integral 1 over 2 pi I times the integral over that closed contour loop of w of t divided by t times t minus z dt, which, given that we just sort of showed that those integrals over the circle contours go to 0, we showed that this is actually equal to 1 over pi times the integral from negative infinity to negative 1 over e of the imaginary part of w of t over t times t minus z. Right, this was the result that we had before, dt. Right, this was the result that we showed before, and the fact that we can just say these two things are equal is because we're able to, more or less just heuristically, show that the integrals over those two circle contours go to 0, and so we're just left with these two line integrals in the plane, which slowly wrapped around the negative real axis around this branch cut from negative infinity to negative 1 over e. So this is all really good looking, it's very promising, and so what we're going to do now is see if we can replace things in here with strictly real numbers that are not in terms of the w function, namely the ones that we established before when we assumed certain things about whether or not the function is imaginary or if it's real.